All right, so now we're going to move on in part 2 of our carbohydrate structure and talk about how nature sort of protects this reactive molecule. We highlighted that sugars in their linear or open chain form, because they have a carbonyl containing functional group that's a carbonyl, either as an aldehyde or a ketone, that's very reactive. And so just like in the organic chemistry lab, if you want to protect an aldehyde or a ketone, you react it with an alcohol and you generate a hemiacetal, a hemiketal, or an acetal or a ketal. Okay, so we're going to see the same sort of chemistry happening biologically. So just sort of going through our reaction mechanism here, I'm just going to read through sort of at the bottom here. Hemiketal formation is found in biochemistry when ketose sugars cyclize. And this is just for a reaction mechanism. For aldose sugars do it as well. But this was actually looking at your carbonyl as part of a ketone. Much as in synthetic organic chemistry, this chemistry helps protect the reactive ketone or aldehyde functional group. So sugars that are in that hemi form, hemiacetal or hemiketal, are referred to as reducing, since they are one ring opening step away from having a functional group which can undergo redox chemistry. That terminology is going to become important for us moving on, understanding whether a sugar is a reducing or non-reducing sugar. We'll use the analogy of tying your shoelaces and then double knotting them. What we'll have is when you cyclize your sugar, what happens is you are knotting your shoelaces. They can come untied fairly easily unless you double knot them. Double knot them is the equivalent of making them into an acetal or a ketal. Tying your shoelaces or cyclizing your sugars are a way of making them into the hemiacetal or hemiketal form. Okay. So just looking at our mechanism here. Now this again was for hemiketal formation because we had our group here was going to be another carbon atom. So that was going to be a ketone. Again, if this is a hydrogen, we'd have an aldose sugar and we'd be forming a hemiacetal. Chemistry happens here oftentimes by protonating that carbonyl containing functional group, making it a better electrophile, making it more electrophilic. Then we have an attack by an alcohol functional group. Again, that alcohol functional group is going to be a nucleophile. Alcohols are not great nucleophiles, so by protonating this carbonyl containing functional group, we create a better electrophile. Nucleophilic attack generates our tetrahedral intermediate. Here's our tetrahedral intermediate, no leaving group that we can have leave there. So this is not like we see when we have reactive functional carbonyl containing functional groups that have good leaving groups like amides or carboxylic acids or esters. Okay, all that we really can do here is we can deprotonate our incoming nucleophile, and in this case we generated a hemiketal. And if this is a hydrogen, it's a hemiacetal. The big key piece here is understanding, well, what if your two groups here were connected together? What if your alcohol was actually part of your carbonyl containing molecule? It's exactly what we have with sugars. Your carbonyl is part of a molecule that has a whole bunch of alcohol containing functional groups. And what we're going to talk about here is there are very specific geometries that will be allowed. It's not every single OH group here that's going to be available to do chemistry. But if our alcohol is on the same molecule as our carbonyl and we do this chemistry, we create a ring structure. Okay, so keep that in mind as we look at what we have here. Now I know this is a very busy slide here, but I want to highlight what's happening. This is what we had on our first slide. Okay, well, our first video there, we were talking about the linear or the open chain forms is Fisher projections of all of our sugars. Okay, so highlighting our open chain forms are only present about 1% of the time. Are they going to be in this open chain form? And that's because that carbonyl containing functional group is reactive. So remember, we talked about glucose and we talked about right, left, right, right. Well, one of the things that I want you to take a look at, and then I'm going to show you a little video here, we're going to have all of these guys are on the right side of your molecule. So this is all on the right side of your molecule. So what I want you to envision is this molecule laying down. So everything that was on the right side now is in a down position. Okay, so everything that was on the right side, that OH group, that hydrogen, OH group, and OH group. These are all in the down position. So I'm going to walk through this first, and then we'll sort of watch a video to sort of think about how this happens. I'm going to zoom in here. Okay, I want to remind ourselves about a couple of pieces here, and I want to sort of label a couple of atoms. Okay, so here we've got this OH group. This OH group is going to be our nucleophile. So just like we saw on that last slide with our reaction mechanism, we have an alcohol that's going to be our nucleophile. And then we've got a carbonyl containing compound that is going to be our electrophile. So here again is our electrophile. So a couple of pieces to highlight that it's important about our electrophile. Our electrophile is sp2 hybridized, so it is trigonal planar. And that is a key piece here. The fact that this molecule has this carbon atom as planar means that there is the ability to attack from the top or the bottom face. So see if this makes sense. If I'm attacking from this bottom face, what's going to happen is when I generate my OH group and I protonate that alcohol, that's going to put that OH group in the up position. Okay? If I attack from the top face, then the rest of this molecule is going to go down and be protonated, and it's going to be on the bottom. Okay? Hopefully what you can sort of see here, I'm going to draw in my nucleophilic attack here. I'm going to draw in my nucleophilic attack, in this case coming from the bottom face. Okay? That's going to mean that when these electrons sort of go and grab a proton to be protonated, okay, that OH group is going to be in the up position. Okay, so this carbon atom here, I'm going to sort of label things. This carbon atom was the one that had the OH group. That's that carbon atom right there. Our OH group that sort of did our nucleophilic attack becomes that oxygen atom in the ring. So this oxygen becomes that oxygen. Okay, I'm going to label here in green this this oxygen atom, okay, becomes that oxygen atom and again gets protonated to make an OH group. That happened because we had bottom face attack. Okay, a couple of things that I'm going to label here, and then we're going to understand sort of the nomenclature that we have here for this sugar. Okay, when we have that OH group on the same side as that exocyclic CH2OH group, we are going to label this the beta anomer. Okay, beta, and you can think of it this way, that these are both, these groups in green are both on the same side. Now, I called these anomers, okay? And why we call them anomers is the position of that OH group, okay, is going to dictate whether it's the beta or the alpha anomer, okay? And so this is the anomeric carbon. Lots of nomenclature here to think about here. So that is the anomeric carbon. You can label the anomeric carbon as the carbon that used to be the carbonyl, okay? So it's always going to be carbon 1 for aldose sugars, carbon 2 for ketose sugars, okay? I'm going to label this new bond that we formed, that bond that we formed when we cyclized that sugar, okay? This I'm going to call the anomeric bond. That's a new bond that's formed to the anomeric carbon when we cyclize this sugar. Okay, so that's how we identified the beta piece, reminding us this carbon atom here is the penultimate carbon atom, okay? That's the carbon atom that we get the D stereochemistry from. So I'm just going to label that. I want you to know where all of these pieces in the name of a sugar comes from. Beta comes from how we did our cyclization chemistry, which face we attacked from, which dictated the position of the OH group on the anomeric carbon. When they are both on the same side, that is the beta anomer. Okay? Now, you'll note here that when we made this arrangement, magic numbers of 5 and 6 when we form rings, right? Because that allows us to have bond angles that aren't strained. So 5 and 6 membered rings will allow us to do that. If you have too much smaller than that, you're going to have strained angle strain, and too much larger than that, well, you're really not sort of setting things up nicely to find one another. So 5 and 6 membered rings are what we see with sugars. I'm going to highlight here, I want to draw a structure of an organic compound. This is called pyran. And you'll notice that this 6-membered ring with an oxygen that's part of the ring looks very similar to what we see as the central core of a sugar, okay, a cyclized sugar. So because this is a 6-membered ring, okay, we're going to call this a pyranose sugar because it's based on pyran. Okay, that was a lot that was there. I'm going to hop over to a video real quick because I want to show you. I'm first going to try to demonstrate it here with my molecules, and we'll see if we can sort of see it here. So here I've got, again, my right, left, right in my glucose. There is my carbonyl containing functional group. I've got an aldehyde there. This is an aldose sugar. So what I'm going to have here, okay, we've got right, left, right. If I'm going to sort of show you what happens here, we're going to lay this molecule down. And then this is my C6OH group. This on carbon 5, this is the one that gets to do my nucleophilic chemistry. So this is going to want to come through here, wiggle. And I'm basically, I don't know if you can see, that's a 6-membered ring that's there. This is going to be the chemistry that happens between this oxygen atom and my carbonyl. Again, if my carbonyl is planar, I can attack from the top face or the bottom face. Okay, I'm going to show you a video here in a second that I found online that I think is going to highlight that. But after we sort of watch that video, then we'll sort of look at what the structure of this will look like. Okay, so I'm going to hop over here just for a second to show that video. All right, so what I wanted to be able to do in having my linear open chain sort of glucose form is I sort of wanted to be able to show you how this could cyclize. I think this little video is going to show us a little bit better. Okay, and we're probably going to play, it's only like 19 seconds long, so I'm going to start and stop it as we go along here. So here we're going to see, here's glucose coming into water, Fisher projection, open chain, highly reactive, right? So there's our aldehyde containing, or our aldehyde functional group there. So carbon 1, 2, 3, 4, 5, 6. So again, we've got our right, left, right that we see. Do we know that this is glucose? Our 5th carbon here, this is the OH group that's going to be our nucleophile. What we're going to see is that carbon being our electrophile. We're going to ring close this. So again, what I tried to show you with this guy is you're going to see on this video, we're going to get, here's our carbonyl. Here is our OH group on our 5th carbon. That's going to be sort of the chemistry that comes together. So we're going to watch this now. Remember when we looked at our linear open chain forms and we talked about cyclizing them, I said we're going to lay them down and then we're going to cyclize them. You're going to see that happen here. Okay, so it's sort of laying down, wiggling. We're going to sort of have atoms come around. I'm going to pause it there. So again, now we've got this set up. So there's our carbonyl, and then we've got carbon 1, 2, 3, 1, 2, 3, 4, and this is our 5th carbon. There's our OH group on our 5th carbon. That's the carbon that is the D configuration. This is our nucleophile. Here's our electrophile. You can already see that it's set up to form a 6-membered ring. But remember, this is planar, so we can have attack from the top face, and that's going to put that OH group down, attack from the bottom face, and put that OH group up. So this last little bit's going to show that. Again, top face and bottom face attacks are going to generate the alpha and the beta anomers. Okay, coming back here now, okay? Here is that cyclized sugar, okay? Got my oxygen in the ring, and I should note by formalism, we are always going to draw, this is what's called a Hayworth projection, okay? We're always going to have that oxygen sort of in the upper right corner of our hexagon that we have there. that's kind of by formalism how we're gonna draw things. Okay, so after we did our cyclization chemistry, okay, and let's see how I'm gonna show this to you here. This, again, there's my oxygen in the ring. Okay, we're gonna look at this in a lot more detail on the next slide. Okay, let me turn this maybe so it's the right way for you. So that oxygen is in the back right corner. Okay, so this is sort of what we have here for our cyclized glucose. You may recognize this. This is a chair. Okay, Haworth projections do not look like chairs. They're much easier to draw than chairs. Okay, but as we're going to see in a minute, it's still going to have sort of this same orientation of groups. So we're going to take a look at that in a minute. But I first want to take a look at, and maybe go a little bit more quickly, what we see with fructose. So glucose and fructose, arguably probably nature's two most important sugars. When we actually put those together, that's how we generate table sugar. Table sugar is glucose plus fructose hooked together. So fructose is the 6-carbon ketose sugar. That's probably nature's favorite. So what happens here is when we take this guy and we're going to lay it down on its side and we're going to cyclize it, okay? What we're going to see here is if we use that same 5th carbon's OH group, what we're going to see is because that carbonyl is one more position in, we don't form a 6-membered ring, we actually form a 5-membered ring. So highlighting again, we are going to use the 5th carbon's OH group. So that's going to be, again, our nucleophile. Our carbonyl is still going to be our electrophile, but it's 1 carbon in. So we are going to have a ring that's shorter by 1 carbon atom. So another planar molecule here, to think about whether we're going to have top face or bottom face attack, I need to look at the configuration of the OH group on my product. Okay, right now I can see that it is on the same side as my exocyclic C6H2OH group. So that again is going to mean that it's beta. In order for that OH group to sort of go up, that meant I would have had to have another bottom face attack. That's what we had up here. It was a bottom face attack. So bottom face attack, again, we're going to grab and protonate that OH group, and we're going to generate the beta anomer. Labeling some of the same pieces that we had here. So this again is our anomeric carbon. 1 position in, so it's the 2nd carbon. Here again was our carbon atom that provided our nucleophile, that's C5. We've got our anomeric bond here. That D configuration is dictated by the position of that, or the stereochemistry at that carbon atom. Okay. If we look at the organic molecule that only has 5 atoms in its ring, that's called furan. Okay, so furan is going to be why this is called a furanose sugar. So it's beta D fructofuranose. Okay, lots of like little pieces of nomenclature that we're going to see here with sugars. Okay, so I want to take my chair here, okay? Because our next slide is going to sort of show us the difference between chairs and Haworth projections. And importantly, I want to indicate the difference between configurational and conformational isomers. Okay, so by just definition, a configurational isomer is one that we must break bonds in order to interconvert. So I want to make sure that you can see this, okay? So here again is my 6-membered ring. There's my oxygen atom. Hopefully for you, you're seeing it in the back right corner, okay? So what I'm going to have here is here is my C6H2OH group, okay? And here is my OH group on my anomeric carbon, okay? Hopefully you're able to see this okay. This is in the up position. So is my C6H2OH group. It's in the up position. They are both on the same side of this sugar. So this again is beta D glucose. If I wanted to make alpha D glucose, essentially I need to change the stereochemistry at my anomeric carbon, which means I'd be switching these two. I cannot do it without breaking a bond. I'd actually have to break my modeling kit, okay? But importantly, if I wanted to actually do it from my linear open chain glucose form, it just would mean that I need to attack from the opposite face. Reminding you here, right? It was a bottom face attack to make the beta anomer. Don't put that association together. That bottom face is not necessarily always going to be necessarily beta. It is for what we see here. But what we're going to see is that we have the ability to attack from the top face. But again, it would be breaking my anomeric bond. So if I want to interconvert between my alpha and my beta glucopyranose, I would have to break this bond, go back to a linear open chain form, and then I would need to reform that anomeric bond. Again, right there, I would need to reform that by attacking from the opposite face. So I can only interconvert those by bond breaking, okay? Now, conformational isomers, conformations, when I was talking about my linear open chain form, and I'm kind of twisting all around here to sort of make the most stable sort of zigzag structure, I was looking at different conformations. I was rotating bonds in order to interconvert these, okay? When we have, and let me orient this so that you can sort of see with my oxygen sort of in the back right corner of what I have here, this is a chair conformer. And in organic chemistry, you learned about chair flipping, okay? So I have a chair conformer. I actually have the chair conformer that I'm going to have on the left here. And maybe you can see this. Do you see how I've got my hydrogens at those positions all pointing down? Do you see them here? 1, 2, 3. All of those hydrogen atoms are pointing down, okay? And then I've got 2 hydrogen atoms that are pointing up here, this guy and this guy. I don't have anything where my oxygen atom is, okay? So that's my oxygen atom. Now, what I want to do here is I want to do a chair flip, and I want you to see what happens here, okay? Right now, maybe you can see I have got axial and equatorial positions. Axial, equatorial, axial, equatorial, okay? What we really see in a Hayworth projection is we don't see axial and equatorial. We just see up and down, okay? Because a Hayworth projection is easy to draw, but it incorrectly makes it look like there's 90-degree bond angles or something, and that's not the case, okay? So what I have here is this molecule on the left where all of my OH groups, OH there, OH there, OH there, okay, OH here, okay, and then my CH2OH group, these are all in equatorial positions. Let's see what happens here when I do a chair flip. Remember, when you have a model and you want to do a chair flip, you just take and you make your head be your footrest and your footrest be your headrest, okay? You probably can even see what sort of happened there. Now, all of my hydrogen atoms are what are in my equatorial positions, okay? All of my bulky groups went to axial positions, okay? You can see that very simply here, right, with that chair that we have drawn, but you probably can see it even more dramatically when I look at my model. Let me flip back here. Let me flip back. Okay, so all I did was rotate my chair. I did a chair flip. Remember what chair flipping does is it interconverts axial and equatorial bonds. Now all of my hydrogen atoms, those 5, I've got 5 carbon atoms that have groups that'll flip back and forth. It's either going to be a hydrogen or it's going to be an OH group, or in this case, it's the even bigger CH2OH group, okay? Chair flip puts all of those hydrogens now axial, okay? Really important thing. I don't think it's coincidental that beta-D-glucose is nature's favorite sugar. It is the only sugar that has the potential to have all of the axial positions with hydrogen atoms. Let's just imagine this for a second, okay? Look at this is again beta-D-glucose. There's my oxygen. This is my anomeric carbon. That's the carbon that used to be a carbonyl. So this is carbon 1, 2, 3, 4, 5, 6 is exocyclic, okay? So let's think about what would happen if we were to make mannose. Mannose is the C2 epimer of glucose. That would mean at my 2 carbon, I need to switch my hydrogen and my OH group. Now all of a sudden I can't have 5 groups be hydrogens in axial positions. I would have 1 group have an OH group that would have to be axial. Same thing if I go not carbon 1, 2, I go carbon 4. That is going to make the C4 epimer of glucose. That's going to make galactose. If I want to make galactose, all I need to do is I need to switch these two groups, hydrogen and OH group. Again, I'm going to have one OH group that's going to end up being axial. I don't think it's coincidental that beta-D-glucose is nature's favorite. It is probably because it is the most stable sugar. It's the only sugar where you can have all of your substituents, your bulky substituents, be equatorial.